Let's talk about physics interviews. I had 3 questions prepared here today for us to talk through that I hope demonstrate the breadth of style of questions that you could be asked, and therefore the breadth in the type of thinking and talking that we're expected to do for a physics interview. The first question I have is very much a simple context with a given outcome that we have to spot. So kind of quite an objective question. There's going to be one right answer. Can we spot that answer? So here's the question. We have 2 identical balls in a room. These balls are completely thermally isolated from their surroundings, so they don't give out or take in any heat by any method of heat transfer. One is sitting on a table, the other is hanging from the ceiling by a string. If we give both of these balls, through some magical process, an amount of heat energy, delta E, assuming they were initially at the same temperature, which one will reach a higher temperature? So take a few minutes here, pause the video, and talk out loud through this problem as if you were actually in an interview. Because discussing physical problems is hard, and communicating your thoughts is hard, and therefore it's a skill that we need to work on, because we haven't really been tested on that at all in high school. Sure, we might occasionally be asked by our teachers, and sure, we might have conversations with our peers about the topic, but realistically, high-level, difficult physics concepts, can you explain them well to someone you've never met? That's tricky, and we need to practice that. So, give it a shot now. What you might find when you try to answer this question is that it's very easy to take shots in the dark. Be like, ooh, is it this? And then kind of hope that you'll be told, yes, well done, you spotted it. The answer to this problem, once you see it, is obvious and inevitable. And until you see it, is quite elusive. So I'd strongly encourage you, if you haven't found something that you're guaranteed sure is the answer, keep looking. Don't stop. Don't be like, yeah, it's probably this thing here. The solution to these problems shouldn't ever feel like that. Maybe it's this, well done. Okay, I don't really understand why, but I guess we're moving on. You can certainly expect that not to happen. You will be pushed to explain why, and the problem should be satisfying and make a lot of sense once completed. So for this problem, both spheres are absorbing some heat energy. We might ask ourselves, why does that not go to temperature? Well, what is temperature? Temperature is a measure of the kinetic energy, effectively, of the particles inside. So we have some initial magic energy that we're giving, which should, we know energy is conserved. This has to go somewhere, but it's being suggested to us that not all of that energy is actually going into thermal energy in the particles. So we might think about other types of energy that could be produced here. Maybe sound, light, gravitational energy. There's a few things we can point out. One thing we need to be vigilant on is staying aware of all physical factors that could be relevant. So here we have a temperature increase. What property of materials do we know is associated with heat increase? Well, actually, volume. Thermal expansion happens in all substances. Most of them expand when they grow hotter. So for these 2 spheres here, we can expect that as they gain energy, therefore as they gain temperature, therefore as they expand, actually their center of gravity is going to change. And this is the key to this problem. The sphere on the table, to expand, its center of gravity must move upwards. Overall, the sphere will be positioned higher. Similarly, this sphere, since it's attached from above, must expand downwards. So the sphere on the left does work against gravity, so not all of that delta E can be converted into temperature, whereas the sphere on the right has work done on it by gravity. So actually, it will wind up with more than delta E as effectively temperature, as its kinetic energy in those particles. So this tells us our answer. The right ball is going to be hotter. Let's look at the second question here. This is also one with a fairly standard route to the answer, although we'll need some physical interpretation along the way. However, it's not necessarily about reaching the answer. There's some maths involved. It's not necessarily about did you do the maths, It's about both how accurate and how fast you were. Again, the physics, it's not did you spot the answer, it's how convincing were you in your evaluation of this being the correct interpretation. Were you aware of the limitations of our model? And did you note them? Did you suggest whether or not they might be significant? So without further ado, here's the problem. We have a square-based pillar of side length just 1 unit. You can imagine this vertically in a room. Now on the base, looking down, we're going to tie a string along with some weight at the end, some mass. At the start of this problem, we're going to give this mass a velocity v, perpendicular to the string. The question is, how much time will it take before the mass collides with the pillar? Now, we don't have all the information here. We might say this length is L. We probably need to parameterize that. And now we need to physically model the problem, figure out what we think is going to actually happen here. So just from kind of our physical understanding of this problem, I think it's clear that, hey, the rope is going to swing around to some extent, isn't it? Certainly, it might swing around in a circular arc here and reach the top. Now, at this point, there is 1 unit of string that now lies along the pillar and length L minus 1 remaining. And at this point, we have a very similar setup to before. Now, one question we might ask is, how do we expect the velocity, or the speed, perhaps, to change in this situation? If we ignore friction from the floor, that's probably fairly reasonable for this problem. Friction is going to be a nightmare to incorporate. Let's solve the problem without it. We can see that the only force on the mass is the tension in the string pointing inwards. And in this case, the speed can't be changing. This is classic circular motion with a force towards the center. The force is simply going to be mv squared over r, and because it is purely perpendicular to our velocity, it can't be changing the speed. So actually, the speed in this whole problem is probably a constant, or at least can be modeled very well as a constant. Now, if we think about successive bits of this journey, well, now that the string is kind of latched on here, our next arc is going to be of this radius L minus 1 and leave L minus 2 remaining. And you can expect here that we get now L minus 3, L minus 4, etc., round and round until we collide with the block. Now maybe here we can just say L, I'm going to assume this is some integer because it makes the maths, I think, a lot easier, a lot friendlier to calculate. So we'll just assume it's an integer, find our solution. If it's not an integer, we can deal with that if the professor asks us to. So let's think about the times involved here. This first arc here is a circle, or at least a quarter of a circle with radius r. So if we want the first time here, t1, that's simply going to be distance divided by time. So distance is going to be pi l over 2, that's a quarter of a circle, and our velocity, or our speed, is v. So we get pi l over 2v. For our second time, well, we said that the only thing to change is the radius of the circle. So this is just going to be pi l minus 1 over 2v. Now similarly, t3 is going to be pi l minus 2. And we can expect this pattern to continue all the way until we have simply 1 unit of string left that has to do that final thing. So we might say t final, or maybe we call this tl, equals pi times 1 divided by 2v. Brilliant. So this puts us in a position where we can actually find the t total. This is just going to be summing up from I equals 1 to L all the times Ti. So T1 plus T2 plus T3 plus T4. If we factor out pi over 2v, in this bracket we get L plus L minus 1 plus L minus 2 plus etc., all the way down to plus 1. Now there's a few ways we could evaluate this. The easiest by far is simply to kind of look at this bracket backwards, because really what we have here is 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus blah 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 all the way up to plus L, which is a classic arithmetic sequence that we should certainly know the sum of. Right? This is just going to be pi over 2v multiplied by half L plus 1. Meaning that we get our final answer, the total time is going to be pi L plus 1 over 4v. In this case, we have a fairly objective answer, but don't underestimate how much kind of style points are present in our approach to that answer, because there's a lot in this problem, and how we lay that out, how we communicate it, how we talk about it, are all very significant. Specifically here, you would not believe the number of times I've seen students take this, which they've undoubtedly seen many times before, sum from 1 to n being half n plus 1, a classic, and find rather creative ways of turning it into something else. So here's our answer. Fantastic. If you made your way through this problem quite fast, you felt quite confident with it, it's very possible that you'll be pushed on an extension to this problem, which we'll look at now. So here's an extension you might be asked on this problem. Could we now sketch the tension in the string as a function of time? So again, I encourage you to take a few minutes here, try to answer this question for yourself. Speak out loud your work and your reasoning as much as possible. So we're certainly going to want to know how the tension changes. Now, luckily for us, the tension is just given by this thing here, isn't it? So if I denote the tension for some part I of the journey, if we index it the same as before, is mv squared doesn't change, and then it just depends on ri, the radius of the string, of the circular motion at any point. Now how this goes, the radius begins at L and drops all the way down to 1. So actually 1 over the radius is going to start at a minimum point, 1 over L, and slowly increase. It's almost as if we're making progress backwards up a 1 over x curve. Because we start at 1 over L, then we go 1 over L minus 1, 1 over L minus 2, 1 over L, etc., and eventually we end up at 1 over 1. So the tension we should expect to be accelerating. And the time, well, we already found the time, didn't we? We know that the expression for the time is pi L over 2v, or pi L minus 1, L minus 2, L minus 3, etc. over 2v. So the time should be linearly decreasing, whereas the tension should be kind of ramping up this 1 over x curve. Okay, it's a little bit tricky. Let's try to sketch it. This sketch does not need to be perfect. 90% of this sketch, in fact, is already done. Our observation of how the tension and how the time changes, already, that's fantastic. I think that's the vast majority of the work done. Our ability to turn that into a sketch, well, we can try. It's certainly not going to be perfect, but as long as it's kind of ish, roughly close enough to what we were saying, we should be fine. So tension accelerating, time linearly decreasing. So I might start with some tension, and that's going to be slowly increasing while the time linearly decreases. Okay, maybe something like that. It's a hard sketch. As long as you have something vaguely like this, where again, the time decreases, the tension increases, we're fine, we're happy. Let's look at our third question here. Compared to the first two, which were more formulaic, this third one is very open-ended. It's entirely up to you to find as many physical factors as you can relevant to the problem and try to model it as best you can. Ultimately, you will fail. This question is so complicated that there's no doubt in my mind, and I also have 50 plus interviews with students, which I can attest this to be true, that you will accurately describe what will happen in this situation. It's not about finding the right answer. It's about how do you think about it? How do you communicate it? How do you reason through these things? So here's the problem. We're going to drill a 1 meter radius hole through the earth, all the way down to the other side. And into this hole, we're simply going to drop a basketball. What happens? Again, talk me through it, or talk the air through it. Talk through your answer as if you had a professor listening to you. Let's try to approach this problem like we would in an interview, by listing relevant factors. So one thing maybe that immediately comes to mind is energy. If we assume conservation of energy, the ball should reach the other side. It should exactly reach the other side. In the middle, all of its gravitational energy will be converted into kinetic energy. It'll be traveling very fast. And exactly at the other side of the Earth, somewhere near New Zealand, actually, if you're in the somewhere near New Zealand, actually, if you're in the UK, we should be stationary once we reach the outside of the Earth. And we might oscillate backwards and forwards here. Now, if you're a very able student, if you are a very keen student and you've come across Gauss's law, you might actually be able to demonstrate that this is exactly simple harmonic motion in this case. If you know how to find the gravitational force inside a sphere. That's extension knowledge. It's certainly not expected, but it would be a great thing to show off here. If you know Gauss's law and you can do the calculation in this case. This is a nice observation to make. Conservation of energy, some kind of oscillation, maybe SHM. Immediately here, I think we can also criticize the model that we've just put forth. It's a great observation for us to make. This is how this thing would oscillate. Also, it's a great observation for us to make. This is not how it's going to work at all, because of course, friction is going to be very relevant here. Maybe just from intuition of physical systems, perhaps you're a football fan or a squash fan, and you know just how intensely air resistance affects fast speeds. I mean, planes fly. That's crazy. That's all about fluids of air, giving lift. So clearly air resistance is relevant. We can't just fall for internally fast velocities. Maybe we could estimate the terminal velocity in air at sea level, atmospheric pressure-ish, maybe roughly between 10 and 100 meters per second-ish. Quite hard to say exactly. Don't need to know precisely where. But if we think about g relative to this, 10 meters per second, clearly, if we ignore friction, we will reach terminal velocity in a matter of seconds. So friction, in this case, certainly is going to matter. And I think we can quite clearly say that if we've reached terminal velocity in a number of seconds, then we're not going to be going all the way to the other side of the Earth. In fact, we're probably going to be falling short part of the way there, and then maybe having some damped oscillations. Let's mention a couple other factors. Heat. The Earth is hot. The Earth is extremely hot. If we put a basketball down there, it would either burn or melt, depending on how much oxygen happened to be present in our tunnel. So heat, certainly relevant. Maybe we have to heat-proof our basketball. Also, pressure. The pressure under the Earth is going to be absolutely immense. The weight of all that rock crushing down, unbelievably strong. So our basketball is also going to pop. Now, does it pop or melt or burn first? Hey, who knows? Certainly, it'll do some of these things. An extremely significant factor as well is that the Earth is rotating. So it really depends on where you drop the ball. To completely neglect this factor, we could drill a hole from pole to pole. And because the Earth rotates around that axis, we wouldn't see any effect of the Earth's rotation. But if we really made this effect a maximum by putting that on the equator, actually gravity would almost become like a centripetal force, and we might get some circular motion, almost orbital solution, where the ball is actually just stuck in the tunnel. and doesn't go further inward to the earth, doesn't go further outward, and isn't in the center of the earth. A huge amount to talk about there. If you're a crazy fan of vector calculus and you've done way too much university level science in high school, which I'm assuming is maximum 1% of successful applicants even, you might be able to do some Coriolis force calculations there. But there's maybe a rough idea of some factors that we could mention here. And again, it's about building a model and criticizing the model as well. It's okay to say, here's my best guess, it's probably trash because of this reason. That just shows critical thinking and awareness. No high school student is expected to have a good understanding fully of how this problem would play out. So do your best. Be critical, be creative, and ultimately try to have fun. The more you can enjoy and play around with the problems, probably the better that you'll do. And everybody walking into that interview room is insanely nervous. It happens. Even the best of candidates, super, super jittery. So don't worry, you're not alone. Yeah. And hey, best of luck.